Hello Hires, welcome to your first video lesson. My plan is to create probably 2 of these videos a week. So what I want you to do, basically everything that I write down, I also want you to write down as well. So can I ask you have a pen, some highlighters if you've got that, obviously a jotter and a periodic table if you've got one. Okay, if you don't, I'll upload one onto my homework website and I'll see if I can get one onto the team's website as well. Okay, so what we're starting with trends in the periodic table, and what we're going to start looking at is atomic size. Okay, so that's our heading for today. Okay, so basically what I get down, you get down as well. Right, so first things first, the size of an atom is indicated by its covalent radius. Okay, and if you have your data book there, you'll find that on page 7 of the data book. Okay, so first things first, we need to know our definition of what covalent radius means. Okay, now this is one of these definitions, very much like homologous series, isomers, isotopes from National 5, covalent radius, you need to know. Okay, so covalent radius is half the distance between the nuclei of 2 of its bonded atoms. Okay, so covalent radius is half the distance between the nuclei of 2 of its bonded atoms. So if I draw, let's draw 2 sort of atoms like that. The covalent radius is that. Okay, so it's half the distance between the 2 nuclei. So the 2 nuclei there and there, so half the distance, that is your covalent radius. Okay. Right, now, what we're going to look at now is the trends that we find in the periodic table. Okay, so there are 2 trends. There is going across a period, and there's also going down a group. And in our National 5 classes, we briefly, if you manage to join the team meeting with your teacher, we briefly spoke about that. Now obviously if you never had me in National 5, it would have been Mr. Wright or Mrs. Clark or Mr. White that did that with you. So there are 2 trends going across a period and going down a period. Now this is the data book, this is page 7 of the data booklet, and I just want us to focus going across a period. So this is the covalent radii of selected elements. So if we look at going across a period, so going from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, what do you notice about the covalent radius. So 134, 129, 90, 77, 75, 73, 71. You'll see that the covalent radius is getting smaller. The atomic size is decreasing. Okay? As we go down a group, what happens to the covalent radius? So 37, 134, 154, 196, 216, 235. You'll see that the atomic size, each atom is getting bigger. Okay, so we're going to write that. So going across the period, atomic size, okay, call that our covalent radius, it goes down. Okay, and again, that is very important. So the atomic size, as we go across the period, goes down. Now, as we go down a group, atomic size or covalent radius increases. Okay, so add that, just put that in a sort of highlighter as well. And you need to know those two trends. So going across a period, the atomic size is decreasing. Going down a group, the atomic size increases. Okay, now I just want you to make a wee sort of note here. Covalent radius is talking about atoms. Okay, so obviously that means they're neutral. The number of protons equals the number of electrons. So that's what we mean by covalent radius. It's talking about atoms. Okay, and don't worry, we will look at ions, but we'll start with atoms just now. Okay, so let's just go for a wee question just now. So write this question down. Why is there no covalent radius for the group 8/0 elements? Okay, if you go back to our periodic table, you see that it's got groups 1 all the way through to 7, but we don't have the covalent radius for group 8. Okay, so what I want you to do is the good thing about these videos is you can pause them, you can rewind them as much as you want. So I want you very quickly just pause the video, answer that question if you can. Okay, if you don't worry, I'm going to come back to it, but I'm going to come back to it at the end of the lesson. Okay, hopefully I remember. I should, but yeah, I'll leave that blank now. You'll only need maybe a couple of spaces for it, so don't worry. Right. So let's go through the trends. Now, we know that as we go across the period, the atomic size is decreasing, but why is it decreasing? Okay, so why does the atomic size, again we're just talking about the covalent radius when we talk about atomic size, so why does the atomic size decrease as we go across the period. Now, what I'm going to give you is a textbook answer. Okay, and basically every single time you do these questions, I want you to write it just like this. Okay, it's a system. We write bullet points, and we get straight to the answer. Okay, so first things first. As we go along the period. Okay, this is when we start our bullet points. A proton is added. Okay, again, if we go back to our periodic table, if we start on lithium, okay, lithium's got 3 protons, but as we go across the period, we add a proton. So 3 protons, 4 protons, 5, 6, 7, 8, 9 protons. Okay, so a proton is added. Now, what that means, if we add a proton, we get a stronger, something that we like to call a positive nuclear charge, and we did speak about that in our National 5 classes if you were in that call. So a proton is added, so this creates a stronger positive, you need to say that word positive, okay, so this creates a stronger positive nuclear charge. Okay, now if we increase the positive nuclear charge, what that does, because there's a bigger nucleus, a stronger nucleus, that's going to pull the electrons in. Okay, so this creates a stronger positive nuclear charge. This pulls, again, that's the key word there, pulls. This pulls the outer electrons closer to the nucleus. And if the outer electrons are closer to the nucleus, this means that the atomic size decreases. Okay, and that there is your textbook answer. You need to get all those points in. So as we go along the period, a proton is added, we get a stronger positive nuclear charge, and then this pulls the outer electrons closer to the nucleus, and then that causes the atomic size to decrease. So the way I like to call this, a wee hint, is think of the 3 P's. Okay, now what are the 3 P's? The first P is, in fact, choose a colour you can see better. The first P is proton, so a proton is added. The second P, this creates a stronger positive, yeah, P for positive, nuclear charge. And the last P, this pulls the outer electrons closer to the nucleus. So when you're doing these questions, always think, right, have I mentioned the 3 P's? Proton added, stronger positive nuclear charge, this pulls the outer electrons. Okay, so always think of the 3 P's. Right, so if we were to call that number 1, let's call that this number 2. Why does atomic size increase as we go down a group? Okay, so again, what I'll do is I'll give you textbook answer. So first things first, always write as we go down a group. Okay. Let's turn to page 8 of the periodic table. As we go down a group, what happens to the number of energy levels? Okay, so we've got 1 energy level there, we've got 1, 2 energy levels there, we've got 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So as we go down a group, an energy level gets added each time. Okay, so I hope you can see that. So we write that as we go down a group, and then let's start our bullet points. An energy, and that's a key word there, an energy level is added. Okay, an energy level is added each time. Okay, so straight away, because an energy level is added each time, the atomic size will instantly get bigger. Yeah? However, there is another point to it. Okay, and what I'm going to do, I'm going to write it down, okay, and then I'll explain it to you with a wee sort of diagram. So, energy level is added each time. Now, what happens, the inner energy levels provide something we call a shielding effect. Okay, so the inner energy levels provide a shielding effect, and what this does, this weakens the force of attraction. Okay, so weakens the force of attraction between nucleus and outer electrons. Okay, so what that means, the atomic size increases. Okay, so that's our textbook answer there, and every single time you get asked a trend question, I want you to be writing this here. Okay, so an energy level is added each time. The inner energy levels provide a shielding effect which weakens the force of attraction between the nucleus and the outer electrons. Okay, now what that means, if we go back to our periodic table, we're going to focus on lithium and sodium. So lithium is 2,1, sodium is 2,8,1. I might actually, yeah, okay. So if we do a wee example, we're going to focus on lithium and what did I say, sodium. So sodium, lithium, sorry, is 2,1, sodium 2,8,1. Okay, so if we have our lithium atom here, we've got 2 electrons and then 1 electron in its outer shell. Okay, if we look at sodium, yeah, same idea. Sodium's got 1, 2, and then in its second energy level, it's got 1, 2, 3, 4, and then we start to pair up 5, 6, 7, 8, and then it's got a third shell, and it's got a shell. Yeah. So just looking at those two, instantly you can see sodium is much bigger. Yeah. Reason it's much bigger, back to our very first point, we've added an energy level. Okay, that's why it's bigger. Now this bit here, the inner energy level, provides a shielding effect. This is where it gets a wee bit harder to understand. Okay, now if we look at Li, that equals the nucleus. Na equals the nucleus. Okay, so there's going to be a positive charge there, and there's going to be a positive charge there. Now, if we look at this, okay, between the positive nucleus and the outer shell, lithium only has one inner energy level. Okay, so lithium's got one inner energy level and it's got one outer energy level. Okay, now if we look at that, if we look at the force of attraction, we can see the force of attraction between the positive nucleus and the outer energy level. Now there's only one inner energy level blocking that. Okay, now if we look at sodium, if we look at the force of attraction, okay, force of attraction, what we've done is we've added an extra energy level. Okay, so we went from 2.1 to 2.81. So that extra energy level, what that does is that's providing a shielding effect. Okay, so that shields the outer electron from the nucleus, and because it's shielding that force of attraction is weaker. Okay, so because the force of attraction is weaker, the nucleus has less of a pull on the outer electron, therefore the outer electron is further away, and that's why the atomic size is increasing. Okay, so going back to this, we need to know that every single time. Okay, so an energy level is added each time. The inner energy levels provide a shielding effect which weakens the force of attraction between nucleus and the outer electrons. Okay, you need to know this bit, so important. Okay, and again, you need to know that an energy level has been added, and you need to know it is the inner, you have to mention the inner energy levels, and that provides a shielding effect. Okay, and then that shielding effect weakens the force of attraction. Okay, now this is your first time coming across this, so don't worry, it does take a while to get used to it, but don't worry, we will be doing question after question after question as well. Right, so what I'm going to do is I am going to do a couple of questions. Okay, so I'll do a couple of questions with you, and then you'll do a couple of questions on your own, and I think we'll probably call it there. I don't want to quite go into ions just now, we'll maybe leave that until the next lesson. Okay, so question number 1. Why in fact, no, go for a harder question. Explain how the atomic size of lithium compares to fluorine. Okay, so if we look at our page 7, there it is, page 7 in the data booklet, the covalent radii of selected elements. If we look at lithium, 134, and if we look at fluorine, it's 71. Okay, so what you'll notice that lithium and fluorine are in the same period. Okay, so you need to ask ourselves, are we talking about protons or are we talking about energy levels? So back to our question. Answer it. Okay, so fluorine, so this is our answer. So fluorine is smaller, has a smaller atomic size than lithium. Okay? Now, that's you've answered the question. However, the question's wanting you, I suppose the key word here is explain. Okay? Now, you've noticed that lithium and fluorine are in the same period, so you need to mention that. So as we go along the period, okay, as we go along the period, what happens? A proton is added. Yeah. What does that proton do? Now remember, think of your 3 P's. So the first P is proton, your second one is positive nuclear charge. Okay, so a proton is added. What does that do? That creates a stronger positive nuclear charge. Okay, and then our third and final P is pull. Okay, so proton, positive, pull. So this pulls the electrons closer to the nucleus. Okay, and because it's pulled it closer to the nucleus, what does that mean? Atomic size decreases. Okay, and again, we've mentioned our 3 P's. We've mentioned that a proton is added, we've mentioned it creates a positive nuclear charge, and we've mentioned that it pulls the electrons closer to the nucleus. Okay? Right. Next question, we'll call this, we'll call that question 1, so call that question 2. How does the atomic size of lithium compare with that of cesium? Okay, and then explain your answer. If you want to attempt these questions before I sort of put the answer in, go for it. Yeah, go for it. Right, anyway, so how does it compare? Let's look at our periodic table. There's lithium, there's cesium. In fact, you know what? I'm going to change that, just for the time being, to potassium. Okay, so there's lithium, there's potassium, and you'll see that lithium's 134, potassium is 196, so potassium is bigger, so we need to write that. Potassium has a larger atomic size. Okay? Right, now explain. So potassium has a larger atomic size. Why is that? Now if we go back to this page here, as we go down a group, an energy level is added each time. Okay, however, because we're talking about going down a group, we need to sort of tweak our answer ever so slightly. Okay, now if we look here, lithium is 21, potassium is 2881. Okay, so I would write that. I would always write your electron arrangement. So potassium is 2881 and lithium is 21. Okay, so potassium has 4 energy levels, 1, 2, 3, 4. Lithium has 2 energy levels, 1, 2. Yeah, so what you have to do, you have to specify how many more energy levels potassium has compared to lithium. Okay, so what we need to say is potassium has 2 more energy levels, like that. Okay, so that's our first bullet point. Potassium has 2 more energy levels. Yeah, makes sense. Potassium's got 4, lithium's got 2, potassium's got 2 more. Okay, so potassium has 2 more energy levels. Now this bit here, I do want to make a wee note because it is important. You have to be specific with how many more energy levels there are. Okay, so again, very important that. Right, so potassium has 2 more energy levels. Excellent. We know that's bigger straight away. However, what does that mean? Okay, so because potassium's got 2 more energy levels, it must have more inner energy levels. Okay, so potassium has 2 more energy levels, more inner, and again that's important, more inner energy levels provide. Can you remember what it provides? Have a wee think. So more inner energy levels provide a shielding effect. Okay, now what does that shielding effect do? The shielding effect, which weakens the force of attraction between nucleus and outer electrons. Okay, so because the attraction's weaker, the electrons aren't pulled as much, so the atomic size increases. And that's it. Yeah. Again. We spoke about how potassium has 2 more energy levels, okay? And those energy levels provide the inner energy levels provide a shielding effect, and that weakens the force of attraction between the nucleus and outer electrons. Okay, so every single time you get asked these questions, you need to be laying it out like this. Yeah, bullet points are the way forward. You don't want to be writing paragraphs. One, I tend to find people write more than they need to. Two, it's easier for the marker to see if you write in bullet points. Okay, so make sure you're doing that. Now, what I want you guys to do, and we're almost there, I want you to do these two questions. See how you get on with them. Okay, so let me get one for you. Question 1, explain why chlorine has a smaller covalent radius than sodium. Okay, and then question 2, I'll go for the exact same thing. Explain why calcium has a larger covalent radius than beryllium. Okay, so guys, try those two questions. Let me know how you get on. Explain why calcium has a larger covalent radius than beryllium. Okay, write out the electron arrangements, see how you get on, and then make sure you're writing in bullet points. If it's going along the period, mention your protons. If it's going down a group, mention your energy levels. Okay, so a wee summary. If it's along a period, it's all about the protons. Okay, if it's down a group, yeah, it's all about the energy levels. Okay, or more importantly, the inner energy levels, because they provide a shielding effect and they weaken that force of attraction. So just like that. Right, before we go, I haven't forgotten this question here. Okay, why is there no covalent radius for the group 8,0 elements? Now, we need to look at our definition of covalent radius. It's half the distance between the nuclei of its two bonded atoms. Now, what do we know about group 8 and 0? The noble gases, they're unreactive, they do not bond. Okay, so noble gases do not bond, therefore can't have a covalent radius. Okay, right, that's us. Thank you very much.